Hey there, and welcome. Today, we are jumping headfirst into the world of complex numbers. And look, if that sounds a little intimidating, don't sweat it. Think of this as us building a brand new mathematical toolbox, one that's going to let us crack open problems that were once considered totally impossible.
So let's get into it. We spend most of our time with numbers on a simple, straight line. Positives, negatives, fractions, they're all there. But what happens when you run into problems that look really simple, but just have no answer on that line? Well, that's when you know it's time to expand the mathematical universe.
So, check out this equation. It looks like a totally standard quadratic, right? Something you've probably seen 100 times. But this one's different. It's our doorway into a new dimension of math because it's hiding a secret that the good old real number line just can't handle.
That's right, you just can't. If you try to solve this with the tools you're used to, you hit a brick wall. You get to a point where you need to find the square root of a negative number. And in the world of real numbers, that's a dead end. The game's over.
But what if we just invented a number to solve the problem? What if we just created it? That is the brilliant, beautiful leap that mathematicians took. They defined I, the imaginary unit, as the square root of -1. And this one idea, it doesn't break math, it completes it. It's the key that unlocks absolutely everything else we're about to do.
Okay, so we have I. Now it's time to build our first proper tool. We're going to call it the complex conjugate. And trust me, this is the secret to taming some of the trickiest things you can do with complex numbers, especially when it comes to division.
And the definition? It's incredibly simple. If you have a complex number with the real part a and an imaginary part bi, its conjugate has the exact same real part. You just flip the sign on the imaginary part. That's it. Plus becomes minus, minus becomes plus. Easy.
You can see it right here. The real part, that's our anchor. It doesn't move. All the action, all the magic happens with that imaginary part. And that simple little sign flip is what gives the conjugate all of its power.
So why is this so powerful? Well, look what happens when you combine a number and its conjugate. If you add them, poof, the imaginary parts cancel out and you get a pure real number. Subtract them, and the real parts disappear, leaving a pure imaginary number. But here's the magic bullet. When you multiply them, you always get a positive real number, a squared plus b squared. This, right here, this is our secret weapon.
All right, time to put our shiny new tool to the test. A division problem like this one, it just looks messy, right? How in the world do you divide by something that has an I in it? Trying to do it directly is a real headache. But with the conjugate, it becomes totally straightforward.
The whole process is just a simple three-step recipe. First, you look at the denominator, 5 plus 3i, and you find its conjugate. That's 5 minus 3i. Step 2, and this is the big move, you multiply both the top and the bottom of the fraction by that conjugate. And finally, step 3, you just simplify. The entire point of this is to use that multiplication trick to turn that messy denominator into one clean, simple real number.
And when you follow those steps, the whole problem just collapses down into something neat. 21 over 34 plus 1 over 34 times I. You see? We took a messy, awkward division problem, and using our new tool, we transformed it into a perfectly normal, complex number. Problem solved.
All right, tool number 1 is in the bag. Let's move on to our next one. We've mastered division, now let's get back to our original mission, solving those impossible equations.
Remember that equation from the very beginning? Let's take it down for real this time. We plug the numbers into the quadratic formula, and just like before, we hit that roadblock, the square root of -4. But this time, we're not stuck. We know that the square root of -4 is just 2i. So we swap that in, simplify the fraction, and boom, there they are. Our two beautiful complex roots. X equals -1 plus I, and x equals -1 minus I. Now hold on, did you notice something incredible about that last answer? The roots were -1 plus I and -1 minus I. They're conjugates of each other. That is not a coincidence. It's a fundamental law of the universe called the conjugate root theorem, and it is an insanely powerful shortcut.
I want you to think of this theorem as a mathematical 2-for-1 deal. Seriously, if you do all the hard work to find just one complex root of an equation, this theorem just hands you the second one for free. It's always just the conjugate. This is an absolute game changer when you start solving even more complicated equations. Okay, here we are, the final section. We've built up our toolbox. We've got I, we've got the conjugate, we have the conjugate root theorem. Now, let's see how they all work together to solve a problem that, at first glance, looks like a real monster. So take a look at this thing. It's mixing z and its conjugate, z bar, all over the place, with multiplication, subtraction. I mean, trying to solve this with brute force would be an absolute nightmare. But we're not going to do that. We're going to be smart.
Okay, deep breaths. The key here is not to panic. This equation isn't asking us to learn anything new. It's a puzzle that's just testing whether we know how to use the tools that we already have. It's a test of our new toolbox.
The trick is to just recognize the pieces we've already learned about. See that z times its conjugate? We know what that is. That's just a squared plus b squared. And see the z minus its conjugate? We know that's just 2bi. So we can just swap those complicated-looking things out for their simple equivalents.
And with that one simple substitution, the whole puzzle box just pops open. The equation transforms into this much friendlier version. Now we can clearly see the real part, a squared plus b squared, and the imaginary part, which is 6bi. The rest is just a matter of matching them up with the other side of the equation.
So we match the parts. The imaginary part on the left, 6b, has to equal the imaginary part on the right, 12. Well, that means b has to be 2. Easy. Then we plug that into the real part. A squared plus 2 squared has to equal 13. That means a squared is 9, so a can be positive 3 or negative 3. And just like that, we found both solutions.
And there you have it. We started with a problem that seemed impossible, and now we're taking apart complex puzzles. So let's do a quick recap of the powerful new tools you've just added to your mathematical toolbox.
So, what's in your toolbox now? First, you've got the imaginary unit I, the master key to this whole new world. Second, the complex conjugate, your multi-tool for simplifying just about anything. Third, the quadratic formula, which is now supercharged to handle any quadratic you throw at it. And finally, the conjugate root theorem, your elegant 2-for-1 shortcut.
You know, we started with a simple little equation that felt impossible. But by introducing just one new creative idea, a whole new world of solutions opened up. It really makes you wonder, doesn't it? What other walls in mathematics that we see as impossible are just one simple, clever idea away from being completely unlocked?